Swayam Prabha. Digital India. Educated India.
So far we have dealt with various problems concerning pressure driven flows and typically in the low Reynolds number regime, and for all these cases we have considered that the no slip boundary condition is valid at the interface between the fluid and the solid boundary. So this is a classical consideration, but if you ask that where from do you know that the no slip boundary condition will be valid always, the answer is not straightforward. I cannot give you just an answer in a single sentence that where from I do know that the no slip boundary condition will be valid. Well, one of the possible explanations that is given by people working with classical fluid mechanics is that when people do experiments with classical systems, macro scale systems, then it is observed that the no slip boundary condition is valid, and seeing is like believing. So if experimentally things are justified and there are virtually no experiments which are dissatisfying those requirements, then that can be considered as like sort of I mean well described boundary condition. At the same time, one when goes down the scale, micro scale, nano scale regime, it is not quite clear that why the same arguments should hold true, and therefore it is important to look into the boundary conditions in fluid mechanics or have a relook into the fluid boundary conditions in fluid mechanics, and typically the no slip boundary condition. So the motivation for this is that we cannot always depend on the no slip boundary condition. I mean there are situations, some of the situations are described in this particular slide, but I mean these are just some typical examples, like not all the rough surfaces hindered the flow. We have discussed I mean quite some time back in one of our introductory lectures that if you have rough hydrophobic surfaces, then actually there may be a thin layer of low density phase that forms on the surface which acts like a friction reducing cushion. So what it means is that not all rough surfaces hinder the flow, and sometimes these can reduce the drag. Super hydrophobic surfaces in nature like lotus leaf can exhibit slip flows. So it is possible that you can have slip flows with surfaces which are highly hydrophobic. That means they have a great phobia for, so the name hydrophobic is quite self explanatory. Hydro means water, so the surface has a phobia for water, it does not like water, so it is a non-weighting surface. So a highly non-weighting surface in nature can exhibit slip flows, and these super hydrophobic surfaces are not just natural surfaces, but you can make artificial super hydrophobic surfaces by using nanotechnology. So super hydrophobic surfaces can be engineered by nanofabrication technologies, and these kinds of surfaces can also exhibit slip. So while I started with a remark that seeing is believing, then if you follow that logic, then these things are also believings, right? These are also certain observations which clearly state that slip is also a possibility. So no slip boundary condition is something which may be justified in many cases, not necessarily that if we get down from classical regime to the micro scale regime suddenly the no slip boundary condition starts becoming invalid, it is not like that, but there may be certain situations when the no slip boundary condition needs to be critically assessed before being used. Now before getting into the slip or the no slip, we will briefly discuss something which is related to the continuum hypothesis. In continuum hypothesis or in continuum mechanics, what we consider? We consider that the fluid is a continuous medium disregarding the discontinuities. So, you typically do not consider individual molecular entities as describing the motion, but it is a collective system that is being described as constituting the motion. So, if you are considering a molecular approach, on the other hand, you are directly analyzing the dynamics of individual molecules. So, in fact, that particular approach is followed in a simulation technique which is known as molecular dynamics. We will discuss about molecular dynamics towards the end of this particular course. Microscopic approach is something which is like sort of a bridge between macroscopic and molecular approach. It does not consider all the individual molecules, but it can represent the statistically average behavior of molecules. So, it is within the paradigm of statistical mechanics or statistical physics. So, that is microscopic approach, where you essentially represent statistically average behavior of many molecules, and macroscopic approach, which is the standard classical approach that we follow in say classical fluid mechanics text, gross average effect of many molecules that can be captured by direct measuring instruments. So, it treats the fluid as a continuous medium disregarding the discontinuity in the underlying molecular arrangement. So, that is this macroscopic approach is also like a continuum approach. So, the continuum hypothesis works, but so this question is important, that we are telling that the continuum approach is a very I mean convenient approach, because we do not have to care about the molecular arrangement and all these things, we just have to consider the fluid as a continuous mass. But when is this approach valid? So, the continuum hypothesis works when there are sufficiently large number of molecules in chosen elemental volumes. So, let me give you an example to illustrate what we mean by this. So, let us say that this is a container, and within this container there is a point at which you want to find out the density of a gas. Okay. This is your problem. So, what you do is that we take a small control volume, and basically you, in the most fundamental way, you try to count the number of molecules what is there inside. So, if m is the mass of each molecule and n is the number of molecules, then n into m is the total mass divided by the volume of the elemental volume, that is the local density. This is a very elementary way of calculating the local density, and you can make this volume very small. Question is how small? If you make this volume very small, then this n will also be very small, and uncertainties in this n will result in a lot of uncertainties in the calculation of this. Let us say that n is large. If n is large, then these molecules are always in random motion. Some molecules are leaving the control volume, this dotted control volume, some molecules are entering that control volume. So, at every instant of time there is a little bit of uncertainty. That uncertainty is a little bit only if the number of molecules is large, but if the number of molecules is itself small, that is say, let us say in this control volume there are 4 molecules on an average. So, if one molecule just goes out, there is a 25% error that comes into the picture straight away. So, if you have sufficient large number of molecules, that is important, but if you have too large number of molecules, then you do not capture the local picture, then you have to consider a picture over a larger region in space, but not a local picture. So, to get a local picture you have to focus on a small volume, but the volume should not be so small that uncertainties for this measurement will become very significant. So, you have to come to a compromise, you have to come to a volume where this small volume, this V in the limit as V tends to V star. V star is basically a critical volume, critically small volume below which the continuum hypothesis will not work, the discreteness of the molecular arrangement will become important. Now, if let us get back to the slide. So, if you see that the continuum hypothesis works when there are sufficiently large number of molecules that we have discussed, so that statistical uncertainties with regard to their respective positions and velocities do not perceptibly influence the average properties, as well as predictions of local gradients. This is also very important. So, whenever you have a property, you also have a property gradient. Now, how do you express the gradient? You want to express the gradient through well known rules of differential calculus, and these well known rules of differential calculus will work only when you can think it as a continuous function. So, the continuum hypothesis should be justified. The second aspect when the continuum hypothesis works is not well discussed always, that is the system is not significantly deviated from local thermodynamic equilibrium. So, this is also a very important consideration. We will discuss about the importance of this consideration when we discuss about gas flows. So, so far in this particular course